Now it's time to take a look at finding some antiderivatives, or finding some indefinite integrals. So problem number 1, we're going to find the antiderivative of 10x dx. So there's a couple different ways that I can do this. Since 10x is a regular polynomial term, I'm going to just use the power rule for antiderivatives here. The 10 can technically be pulled out in front, but it doesn't have to be, so I'm going to just leave it there. Alright, keep in mind that this is 10x to the first. So if I want to find the antiderivative of that, keep the 10, keep the x, add 1 to the exponent, and divide by the new exponent, and put a plus c at the end. If I simplify that, 10 divided by 2 will give me 5x squared plus c. Now remember, you can check your answer by finding the derivative of your answer, which is what I'm going to walk you through right now. If I find the derivative of 5x squared plus a constant, derivative of 5x squared is 10x, the derivative of a constant is 0, so I get 10x, which is what my integrand was. So this checks out. Problem number 2, find the antiderivative of 3y squared plus 5y minus 2 dy. So see how I have y's instead of x's? Because I have dy at the end, that's okay. As long as the dy at the end matches the y's inside, it's a problem that I'll be able to do without any trouble. I'm just going to have y's in my answer instead of x's. I'm going to treat this the exact same way that I treated example number 1. I'm just going to look at each individual term one at a time. So when I look at this, let's look at 3y squared. Keep the 3, keep the y, add 1 to the exponent, divide by the new exponent. So those 3's are going to cross off. Plus, now I've got 5y. Keep the 5, keep the y. That was y to the first. So I add 1 to the exponent, 2, divide by the new exponent. Unfortunately, that fraction doesn't reduce. Now to find the antiderivative of minus 2, well, minus 2 is a constant. The rule said that the antiderivative of a constant is the constant times the variable. And then I have to add my constant of integration at the end. So my final answer here is going to be y cubed plus 5 halves y squared minus 2y plus c. Now let's take a look at an example 3, which has trig in it. Notice all your variables are theta, and at the end you have d theta, so you have thetas in all of your answers instead of x's or y's. Think about what the antiderivative of cosine theta is. The antiderivative of cosine is sine, so the antiderivative of 4 cosine is 4 sine. So this problem starts off with 4 sine theta. I'm going to write minus 7, and now I need to figure out what's the antiderivative of secant squared. Well, the antiderivative of secant squared is tangent, so this is minus 7 tangent theta. Then I have a plus c at the end. And again, I can check my answer by doing the derivative. The derivative of 4 sine theta is in fact 4 cosine theta. The derivative of 7 tan theta is in fact 7 secant squared theta. And then if I have the subtraction in between, I get what I started with. Many antiderivatives require some form of a rewrite in order to use one of the properties that we talked about in the previous video. This is an example of that. There was no rule that said what to do when the variable was in the denominator of a fraction. So the first thing I'm going to do here is rewrite this as the integral of 6y to the negative 5th dy. So negative exponents are going to play a very important role when you're finding antiderivatives. Now it's a power rule type problem. Since the 6 is a constant, it's just going to stay there. Keep your variable. I need to add 1 to the exponent, so negative 5 plus 1 will give me negative 4. And then I need to divide by the new exponent, negative 4. Add on your constant of integration so you have the general solution. And now I just need to clean it up a little bit because I can't keep a negative exponent in my final answer. So for starters, 6 over negative 4, well, that's negative 3/2. And then I have y to the negative 4. Well, if I have y to the negative 4, that really just means I have y to the 4th in the denominator. And then plus c. So the antiderivative of 6y to the 5th is negative 3 over 2y to the 4th. Keep in mind, I don't really care if the negative is up top with a 3, or in the bottom with a 2, or out in front overall. As long as your final answer has that negative in it for the constant, or the coefficient rather, you're all set. But keep in mind, negative exponents cannot stay in your answer. You must have only positive exponents in your answer. Okay. We have 2 examples left to do, both of which require some form of rewriting before I use my antiderivative rules. Problem number 5. Find the antiderivative of the square root of a times 3a minus 4, with respect to a being the variable. There was no rule for a square root, so the first thing I'm going to do when I rewrite this is say, alright, the square root means a to the 1/2. And then I have 3a minus 4 dA. There's also no rule for a product of 2 functions. There was a rule for a sum or difference, but not a product. So the next thing I need to do is distribute. So a to the 1/2 times 3a to the 1st, add the 2 exponents and you get 3a to the 3/2. Then I'm going to have minus 4a to the 1/2, close the parentheses, dA. Keep in mind that dA needs to stay there. Whenever you have an integral sign, you have to have a variable of integration written at the end. They're kind of a package deal. Now I can apply the power rule to find the antiderivative. So the antiderivative here, keep the 3, keep the a, add 1 to the exponent. So 3/2 plus 1 is 3/2 plus 2/2, 5/2. And then I have to divide by 5/2. We'll talk about how to do that in a second. Then I have minus 4a to the 1/2. Again, I'm going to add 1 to the exponent to get 3/2, and then I need to divide by 3/2. Don't forget your constant of integration at the very end. So, how do you divide by a fraction again? Well, to divide by a fraction, you multiply by the reciprocal. So, this is really 3a to the 5/2 times 2/5. And that means I have minus 4a to the 3/2 times the reciprocal of 3/2, which is 2/3. If I put it all together, my final answer is going to be 6/5 a to the 5/2 minus 8/3 a to the 3/2 plus c. If you want to write it with radicals, you can, but this answer with fractional exponents is perfectly fine with me. All right, we have one example left. Here we go, problem number 6. So I want you to keep in mind that this problem will work very similarly if it was x squared plus 2 over, say, x cubed instead of the cube root of x. But what I need to do is I need to get rid of the fact that I have a variable in the denominator of a fraction. So my rewrite starts with, first and foremost, okay, let's get rid of the radical. X squared plus 2 divided by x to the 1/3. And now I'm going to rewrite so that I don't have a fraction anymore. I'm going to subtract exponents and write this all as one line. So 2 minus 1/3 is 5/3. This is x to the 5/3 plus 2x to the 1/3. And now I can start using the power rule for antiderivatives to find the actual antiderivative. So keep the x, add 1 to the exponent. Since it's 5/3, add 3/3 to get to 8/3. Divide by 8/3. But we said earlier, dividing by a fraction is the same as multiplying by its reciprocal. So instead of writing x to the 8/3 divided by 8/3 and then writing this later, I'm going to jump to that step where I'm multiplying by the reciprocal instead of dividing by a fraction. And now for the next one, I have plus 2 x 1/3 plus 1 will be 4/3. And again, I'm going to multiply by the reciprocal of the exponent instead of dividing by a fraction. Don't forget your constant of integration at the very end. Now let's just clean it up slightly. We're going to have 3/8 x to the 8/3 plus 2 times 3/4 would be 6/4, which is 3/2. X to the 4/3 plus c. And again, I don't mind if you leave it with all fractional exponents as final answer. I just don't want to see any negative exponents in your final answer. Fractional exponents are fine. If you prefer radicals, that's okay. Just be careful when you're converting back to radical notation. Alright guys, I hope these examples were helpful in finding antiderivatives.